Okay. You are given an n-player game. What have you got? You've got a bunch of strategies that are given to you, finite set of strategies here, which we call pure strategies, as opposed to mixed, right? That's the terminology. Now we are looking at strategy profiles. I have the stick. Nice. Okay. So I can throw it at somebody if it gets nasty. Okay. So remember that we are also looking at profiles. Profiles means these tupular strategies. Basically, everybody has picked what strategy they're going to play, the pure strategies, and you are looking at what will happen, right? And then this gives us a play, and this is the idea of a normal form or strategic form game, which is just a one shot. Everybody has picked their strategies. That means all you have got now is to give the outcome. So, and you got a payoff function, which for each player, this should not be SI, this is S, right? For the entire profile, it gives you, so this is not SI but S, right? So it's the payoff for player I given this profile of strategies. For every combination, it gives you. So that's the matrix, right? This is the matrix. Assumption is that every player prefers to maximize her own payoff. Okay. No. Okay. So what is the idea for mixed strategies or randomized strategies? A mixed strategy for a player I, when you are given the pure strategies, is a probability distribution over SI. So basically it's a vector, right? For each of the pure strategies, it tells you what's the probability that you play it, right? Basically it's a set of real numbers in the interval 0, 1 which sum up to 1. Yeah, this is what you have got. So basically player I uses randomness to decide which strategy to play based on the probabilities in Xi. So this is the idea. All this we talked about, right? And now let's say that Xi be the set of mixed strategies for player I. So the profiles that you are looking at is the product of these. Okay. So that's why I said notationally it gets messy, so I thought I would bring this, but I have no idea what happened to the file. This is some old, it's not even document class, it's the from the document style world. So I shouldn't have recompiled it, so something went wrong with that. Okay. So X denotes the set of all possible combinations or profiles of mixed strategies now. So this is the space that we are looking at. Note that it's a very rich space, right? Even for two players, what are we talking about? Look at n equal to 2, what are we saying here? These vectors are as rich as ever, right? It's as many strategies as you've got. So even if you're talking about 2 by 2 games, each player has 2. Yeah, so if look at that situation where let's say M1 is 2 and M2 is 2, right? So what is this talking about? It's a pair, right? With probability P I play one and 1 minus P I play the other. That means you're talking about a line, right? You're talking about a line in R2. Isn't that clear? You're talking about something like this. Right? X times P plus X1 times P plus X2 times 1 minus P. If it is 3, you're talking about something of this kind. Region like this. Yeah? So that should be there in your head when you think about these things. Okay. So once you have a profile of mixed strategies, what is the notion of expected payoff, right? Well, take a pure strategy, take a pure profile S1 through Sn and combination of pure strategies. For this particular pure strategy, look at you are playing according to this profile of mixed strategies. What is XFS? The product of, take for player J, this is the probability with which the player J is going to play this particular pure strategy, right? If you take this, right, player 1 is going to pick this with probability S1, player 2 is going to pick this probability with S2, and so on, right? Look at this vector now. So this is the probability of the combination S under the mixed profile X. That should be X. Yeah. Is it okay? This is the so the Xi is giving you the probability for player I's choices. Now I am taking a pure strategy profile. XFS gives the probability of this particular combination being picked, right? That I pick confess and you pick deny, for instance, or right? I pick inspect and you pick cheat, etc., etc. What's the probability of that? Now, assuming that now the product is because we are assuming that players make their random choices independently. That's what I said. This is the model that we are looking at, where everybody has decided their strategies, everybody has decided their mixing, come to the table autonomously, independently, they have made their choices and do, right? Your analysis has to reflect the kind of model that you've got, right? That's the independence that you have. So what is the expected payoff for a player I under such a profile? So this is the UI of X is given by, well, look at the utility for, utilities are always given for pure profiles, right? Remember that the payoff matrix is given to you for pure profiles. Is it clear? That's how the matrix is given, right? These are my pure strategies, these are your pure strategies, and the matrix entries will give you this, right? Now weighted by the probability of that particular profile occurring, which is what you're talking. Sum over all pure profiles. Is this clear? So this is the expected payoff, right? Take the payoff, multiply by weight by the probability, sum up, and you get. So this is really what every player is trying to get the best of. Yeah, any questions? Is it clear? But this is the object that we are going to keep manipulating. Okay. So once again, so the expected payoff is this. What is this? This is the weighted average of what player I can win under each pure combination, weighted by the probability of this combination, right? So this is this notion of weighted averaging that is central to this whole business, and that is a connection with all optimization problems that we want to work with. So what's the key assumption here? Every player's goal is to maximize his own payoff, and as I said, this assumption is often dubious, and you can have a lot of interesting things thinking of real situations where life is slightly different. Okay. So let's now get to notation. So now we can actually, given something like this, we can define a pure strategy, right? It's though we of course approach the things the other way. Mixed strategy is a more general concept. Pure strategies are those where, what are pure strategies? Where exactly one choice is set to 1, all the rest are set to 0, right? That's the notion of, that means I'm playing this with probability 1, on all the rest I'm set. So making a choice amounts to this. This is convenient to think in these terms because you are saying these are the basis vectors, right? These are the basis vectors, no? Exactly one, 1 in one of the coordinates and 0 in the rest. So we are talking about taking the basis vectors, which are the pure strategies, and forming convex combinations, right? Is it clear? That's what we are doing? That if there are only 2 choices, you can see that, right? So you're talking about p times 1 0 plus 1 minus p times 0 1. There is a picture here. Yeah. So in general, in m-dimensional space, you are picking convex combinations, right? So all the vectors that we are talking about, and so okay. So what is this pure strategy pi ij? It's a mixed strategy which does not randomize at all, right? It picks exactly with probability 1, exactly one strategy from the set of pure strategies of players. So now this is another useful notation. x minus I. X minus I stands for the n minus 1 tuple where you have fixed the strategies for everybody else, the profiles for everybody else, and omit for yourself, right? Denotes everybody's strategy except that of mine. So far I was only talking about 2 players, so I can always use sigma and tau to say sigma is my strategy, tau is yours, right? So I need some way of talking about the opponent strategy. There is no single opponent here, right? It's everybody else. So this is just a notation for that. The strategy of everybody else. Why is that? Because in Nash equilibrium, what's the notion of Nash equilibrium that I introduced yesterday? Yes? For 2 players, what did I say? If you play tau, sigma is my best response to you, and if I play sigma, tau is your best response to it. Then you say that the pair is in Nash equilibrium. But if there are n players, how do you say it? Well, assume that everybody else plays strategy, let's say pure strategy, S1 to Sn, without mine, and Si is my best response to it. Then symmetrically it is true for everybody, then it is Nash equilibrium. So that's the reason for even introducing a notation like this. Okay. So by abuse of notation, what we will do is to use this notation. What is this? X minus I, yi. This is the strategy where I take the mixed strategy X, take the strategy profile X, and where I keep everything else the same for the others, only for mine I am replacing yi. Basically, keeping the other strategies fixed, I want to vary mine to see which is the best response, right? That's why this notation. X minus I, yi stands for fixing everybody else's to X and varying mine to Y. Clear? So this is a term that is seen a lot in game theory, and Soumya and I have done a lot of work on our own work on switching strategies. Switching doesn't mean really like you are following one strategy and halfway through you go to another and so on, right? Strategy switching is something that you will find in all game theory textbooks, but it only means variation in the space of strategies, that's all, right? Very often transformations and stuff. Okay, but normally this is what is called switching from xi to yi. Basically all you mean is that I keep all the other parameters fixed and I am varying mine. Okay, mixed strategy is the best response to, so this is the central notion for which you are doing all these things. When do you say a particular mixed strategy Zi is the best response for player I? Best response is always to other strategies. If I give you an n-1 tuple of strategies, this is my best response. If for all yi, I vary over my choices, this is the best utility that I can get, right? I look at the payoff for Zi that is greater than or equal to the payoff for all other those things. So I keep the profile fixed for the rest of the guys and vary mine, and I find that this is the maximum. This is a maximum. Then I will say it's a best response. It's greater than or equal to, so there can be several possibilities, right? Is it clear? Okay. So clearly, if any player were given the opportunity to cheat and look at what other players have done, right, then she would switch her strategy to a best response, right? Now by the rules of the game, everybody picks their strategies simultaneously. It's not that you. So suppose somehow players arrive at a profile where everybody's strategy is a best response to everybody else, then no one has any incentive to change the situation. So this is what is called a stable state or an equilibrium state, and this is what we call Nash equilibrium. After Nash in 1951 defined this notion. So for a strategic game gamma and a strategy profile given as follows, it's a mixed, as we say, mixed Nash equilibrium if for every player I, xi is a best response to x minus I. Formally, what we are saying, for all I, for all yi and xi is in fact the maximum utility as opposed to all of them. This is simultaneously for all of them, and this is the important point. Yeah, is the notion clear? I introduced it yesterday, but this is just the formal details. Yeah. So in other words, no player can improve her own payoff by unilaterally deviating from this mixed profile. I don't have any incentive to unilaterally choose something else. Something else here is Very important, because what you are saying is it's not that I'll move to a different choice among my things. It also means that I don't have any other, I will not play it with a different set of probabilities either, right? This choice that I have got gets me the best, symmetrically for everybody, right? And we say it's a pure Nash equilibrium if each of these is a pure strategy. Right? And this is what we saw. For instance, in the TV game, there were two pure Nash equilibria, right? Both choosing IPL or both choosing that serial or whatever, right? So pure Nash equilibrium may exist, right? And in that restaurant, there was that pure Nash equilibrium of choosing to serve bad food and the other fellow refusing to buy it. That's a Nash equilibrium and so on. So, of course, what does it mean? There are many interpretations, and the theory is rich with all these things, but this is only the formal underpinning. Somebody is interested, ask me and I'll explain. Okay, now comes an extremely important condition. What Nash in his paper states is an obvious fact, and it is very straightforward, but actually forms a very important observation. So this is the observation. You say best response to x minus. What I say here is, I'm being very sloppy. Take a vector x. I'm saying xi is a best response to everybody else for player I, if and only if, look at the probability of, suppose J is a pure strategy, there is a choice I have got, right? If the probability is greater than 0, that means it is in the support, right? Then the expected payoff I get, right, for that one is actually the maximum of the expected payoffs I can get for all these profiles. This is something extremely interesting. Again, think of it in the two-player case, right? I'm making some choices, right? Now, look at this vector that I've got, x, right? I'm picking one choice with some probability, another with some probability, etc., etc. Some of them I set to 0. That means I don't want to choose them at all, right? It's a mixed strategy in general, can be like that, right? But the moment I have got some of the probabilities are assigned non-zero, something is positive, right? If it is a best response at all, it means that must be giving the maximum utility. That's what it is among these. Now, why is that true? This is not obvious at all, but if you think about it a little bit, you will see why this is true. So what is this? This is what is the expected payoff? The expected payoff is the weighted average, right, over all the probabilities that you've got. Now suppose use the maximum that I could get, right, among all these things. For all these combinations, let's say that use what gets me the maximum. Then what I can do is to rewrite the above, this sum as xs times ui is written as u minus ui. I have just rewritten it. Now what I can do is to distribute, right? The first term I'll get xs star times u, but if I simply take the probabilities over all of these, this is 1. Okay, so this will simply come out to be u. So the first term will come out to be u, and the second one I am taking the x's and multiply over this u minus ui's, right? This is just a rewriting of that same term. Yeah, but look at this term now. This is always going to be non-negative. This is going to be greater than or equal to 0, right? And look at this. This is u is the maximum that I can hope to get. So u minus ui is always going to be non-negative as well. So this term is always going to be non-negative. So that means that ui of x is always less than or equal to u, right? And when will it achieve the maximum? When that sum is 0. So very simple. So all you are saying is, of course, if it's the weighted average, right? The weighted average achieves its maximum in the support. Okay, so this is a elementary probabilistic understanding of probabilities. So it's the weighted average of these. So in particular, therefore, consider in a Nash equilibrium. In a Nash equilibrium, if I find that I've got a profile which assigns some non-zero probability to a pure strategy, then that pure strategy itself is a best response to the rest. This is what it means. Okay. So this is a fairly non-trivial and useful information. So useful in computing Nash equilibrium because, again, think of in the 2% case, right? Now, if you look at the support in the Nash equilibrium, right, I know that my pure strategy is a best response, right? So to check if something is a best response, I need to check only m of my strategies, right? I've got m choices, I need to check only those at most. So it provides a very useful tool in computing this, but this is a post facto thing, right? But of course, this is assuming you find a Nash equilibrium, right? So when you're looking for a Nash equilibrium, this becomes an important condition. So geometrically, it also means that when I'm searching for equilibria, the extremal points that I'm working with play an important role. That's one reason why. But this is the most important. I mean, you just have to look at the statement. I think that the statement is the important thing. So when x is a best response, it's straightforward, and I mean the other way, yeah. Yeah, the other direction I have not mentioned, but that's trivial, right? This is indeed the maximum expected utility. That is going to be the best response for FWT. So it's an if and only if. Any questions? Because of this slide nonsense, if I'm going too fast, please stop me. It's no problem. It's just that there's a lot of writing and I wanted to save some by my laziness, but okay. This is purely formal as opposed to the intuitive arguments we have been doing so far. Okay. So now the Nash's theorem. So this can, with some justification, be called the fundamental theorem of game theory. What does it say? It says every finite n% strategic game has a mixed Nash equilibrium. And he used a fundamental result from topology to prove the theorem, namely the Broward fixed point theorem. That's the proof I'm going to present. This is in fact straight from Nash's 1951 paper. Now there are slightly simpler proofs which use what is called the Kakutani fixed point theorem for those who like topology. So there are, other proofs as well, which are somewhat smarter proofs actually. But this is a very nice proof and I like it. So what is the Broward fixed point theorem? So how many people have done courses in topology? And then you've seen proofs of Broward fixed point theorem and must have seen. Have you seen Broward fixed point theorem? Oh, you're not? That's a bit surprising to me. But anyway, okay. So there is a very nice way of understanding what it means in R2. What is R2? A sheet of paper as far as I am concerned, right? So except that the sheet of paper extends forever, but for our experiment, so let's say two identical rectangular sheets of paper, right? Make sure that neither sheet has any hole in it and that the sides are straight. For topology, these things are very critical. So okay, so neither of them is, they're clean sheets, right? Now name each point on both sheets by its xy coordinates. Of course, for us to do it's difficult because this is the real space, right? On sheets, they are not infinitely dense, but let's assume that, right? So I'm saying that think of your sheet as having grid points and also all the points in between, blah, blah, blah. So that if I put a dot on the paper, I can talk about its xy coordinates meaningfully, right? I hope that makes sense, right? So I can name every point, right? Now, take the two sheets, crumple one of the two sheets in any way you like. Just take it and crack like that. But make sure you don't tear it in the process. As I said, you shouldn't introduce holes, right? So just place the crumpled sheet completely on top of the other flat sheet, okay? Now, the way I like to do it is to first start with the two sheets and just throw lots of points, ink, right? Lots of ink, and name them sufficiently close. You can write, in fact, with good approximations. Now crumple it and place it on top. And this is what the theorem says. Theorem says that there must be a point named AB on the crumpled sheet that is directly above the same point AB on the flat sheet. Comes exactly on that sheet. That's what it is. There must be at least one point. Now, this fact, of course, in its more formal and general form, is the key to why every finite game has a mixed Nash equilibrium. Try it and see. It's a lot of fun. And of course, if you do it with many colored ink, in fact, you can even try to see whether, and that's also a corollary of Broward's 6-point theorem. Because how many colors? You're going to have only finitely many colors, no? So one of the colors, you will get a colored point with exactly the same thing. Except that you must, when you start, you should have sufficiently rich set of this. When you actually play the game, I mean, do this experiment, I've tried this now with just 2 or 3 colors, and if you have about 30-40 points, for sure you'll find one. I mean, theorem says that there exists one, and that might be anywhere, but this is just an experimental thing. Not that it verifies anything, but it's to give you a clue about what's going on. Now, what's going on here? I said that you have to take a sheet of paper with no holes, etc., etc., right? What does that mean? The continuum is a good case, because we have to make it precise. And what is this notion of crumpling the sheet? Some transformation on that space, some operator on that space. That's what you're talking about. You're applying one, and what you want it to be continuous, you want it to be blah blah. We'll see what those conditions are. And then it says that this idea that it comes directly on it, it basically says that it has a fixed point. Okay. So what is the formal statement? Just, is the experiment clear? The crumpled sheet experiment? Think about it. Maybe post facto after you hear about the theorem. Okay. It just had its centenary, the Broward theorem. Okay. It says that every continuous function f from a set to itself, mapping a compact, convex, and non-empty subset of R to Rm to itself has a fixed point. That means there exists some x star such that f of x star is equal to x star. The notion of fixed point, of course, is clear. What are the conditions that you are posing on this? You must start with some subset of Rm, which is compact, convex, and non-empty. Let's see what that means. Is the statement clear? Provided, of course, if you know what these terms mean, fine, otherwise. Remember that convexity is something that I've built into the whole business. When I'm taking with probabilities, I'm always working with convex combinations. Right? Yeah. What are these definitions? For those who know, it's fine. Yeah? Any questions? Questions, comments, whatever? Okay. A set is convex. When do you say a set is convex? If I pick 2 elements and take any linear combination, right? I can define it for, I've defined it for 2. You don't need to, in general, you can define it for any finite collection of points, right? But take anything in the real interval 0, 1. This is enough for us. This is the only definition that we need, right? Lambda x plus 1 minus lambda y should also be in that set D. And this is exactly the line that I was talking about here, right, in this particular case, R2. And in general, D is compact if it is closed and bounded. This is this is the definition that we use here. What is the notion of something being bounded? It's bounded if there exists a non-negative integer which acts as a kind of envelope, right? You are working in Rm, that's why I'm taking something in minus k, such that. So it fits inside a box. This is the geometric picture. Right? The set D that we are picking is, you take an m-dimensional box and I can bound it inside that. There is an upper bound for all the elements. And you say it's closed if whenever I take any sequences, any sequence x0, x1, if each of them is there, then there exists an x in the element which is a limit. So every sequence in D has a limit in D as well. This is the standard notion that you have. So sequence of points in D, then the sequence has a limit, then the limit is also in D, closed under limits. So, and lastly, you say it's continuous at a point, you know the epsilon delta definition. If for all epsilon greater than 0, there exists delta such that if it is within delta distance, then distance of fx y is less than epsilon. If it is continuous, if it is continuous at every point. Okay. Note that in Broward's fixed point theorem, every condition that is imposed is necessary. What, if you want, I'll go up. Yeah. What is the statement? Every continuous function mapping a compact, convex, and non-empty subset to itself has a fixed point, right? So all these conditions are in fact necessary, and we can just see why. Yeah. Look at this map, fx equals x plus 1 on R, right? Clearly it's continuous. It's defined on R, which is closed and convex, but it has no fixed point. Why? Well, in this case, compactness is violated. The set R is not bounded. Okay, it doesn't fit inside a box, right? So this is a function. So this is boundedness is necessary, is what I'm saying. Everything else is there. So what about this one? Mapping the real interval 0, 1 to 0, 1, the square map. It has fixed points 0 and 1. But the moment I define it on the open interval 0, 1 to 0, 1, right? It's a continuous function, but has no fixed point. What's the problem? This is not closed. I mean, I've taken an open interval 0, 1. Of course, it's not closed. So hence not compact. Compact means it should be closed and convex, right? Closed and bounded. Yeah. Okay. So look at this. On the two element set 0, 1, right? F of x is 1 minus x. It has no fixed points. But then this is not convex, right? For convex, you want all the intermediate points also to be there. This is just a two element finite set, so it's not convex. So convexity is necessary. Lastly, continuity is necessary. So look at this map from the real interval 0, 1 to 0, 1, which says for the first half interval, I give the map, I give the answer 1, and for the second half, I give the answer 0. This has no fixed point, but then it's not continuous. In fact, at point half, it's not continuous, and that's enough. Yeah. So all these conditions are necessary, and but as far as we are concerned, we just want to use this fact that it has a fixed point. So what is the strategy? The strategy, oh, well, I think I have it written also. So what is the main idea? Consider the interval 0, 1. It's compact and convex. In general, if I take 0, 1 to the n, it's compact and convex. So basically that means that the set of profiles that I'm going to look at is a compact and convex subset of Rm. Okay. Right. So all we need to do is to define a continuous function from the space of profiles to itself and show that whenever it has a fixed point, then it must be a Nash equilibrium. Broward would assure you that such a fixed point exists. That means you will be able to show that Nash equilibrium exists. This is the idea. You have to design a continuous function on the space of strategy profiles. Broward would tell you that there is a fixed point, but you would have designed your function in such a way that every fixed point would yield an equilibrium. In fact, you don't need to every fixed point, even one fixed point is. But since Broward only says there exists a fixed point, I'll make sure that every fixed point is an equilibrium. So if there exists a fixed point, equilibrium exists as well. This is the idea. So all we need is one direction, but we'll set it up in such a way that x is a Nash equilibrium if and only if it's a fixed point. Yeah, that's what I just said. Is the idea clear? So this is the application that we are looking for. So all the rest of the stuff is into the fact that we are going to use probabilities, right? The moment you decide mixed strategies and I'm looking at mixed profiles, the rest of it comes for free. You just have to design the continuous function. Now, this is where that little best response condition that I was talking about comes of use, that useful fact that we saw. What was that? Whenever something is a best response, that means whenever you are talking about an equilibrium situation, if for pure strategy I have assigned a non-zero probability, that is in fact going to give me the best payoff, right? The pure strategy itself is the best response. This is what we talked about. So that's basically the idea. Okay. So the claim is that take any profile. A profile, now this is really only a restatement of the Nash equilibrium idea, except that I am going to only put pure probability, pure strategies here. Okay. So what does this say? A profile is a Nash equilibrium if and only for every player I and for every pure strategy pi ij, right? Take the opponent's pure strategies, right? Then if you look at the utility that I get at Nash equilibrium, it's going to be greater than or equal to all these. Now this is straightforward. At equilibrium this is straightforward because you know that at equilibrium this is the best payoff I can get anyway. The converse is the statement that is being proved here. So if X is a Nash equilibrium, the inequality is obvious, but conversely look at it. For the other direction, note that what is, in general, what is this, if I look at this, right? Yeah. What is the utility that I get? Fix all the others equilibrium strategies, right? This is the x minus I star. And look at what I'll get for xi. This is given by the sum over, these are all my choices. What's the probability with which I play it times the probability with the pure strategy for the others, right? I have fixed for all these and I have, right? Because my choices, I am going to pick jth element with probability xij. So I just have to do this. So this is really the sum that we are talking about. So the payoffs of player I is the weighted average of the payoffs of each of your pure strategy weighted by the probability of that strategy, right? So clearly this is going to be, you know, that's what we are saying. So if this is greater than or equal to this, then what you have got is a Nash equilibrium, right? This is in fact my best response to everybody else. That's all I need to prove, that this is indeed a best response, which is what we argued in the other statement, that proposition. Yeah? Is it clear? Any questions? You please ask me. So that condition characterizes Nash equilibrium. So the function that we are going to design is going to keep track of this. That's the idea. So I know that at equilibrium I'll get here, this condition will be satisfied. So whatever x that I am considering, I want to see how it will behave vis-a-vis where I want to get to. I need to measure it somehow, where I am relative to whatever is optimum. The optimum I don't know where it is, but I need some way. Okay. So this is what, okay. So what have I done here? I have just rewritten it as the sum of the probabilities here. Now by assumption, for all pure strategies, I know that this is the condition that's given to me, right? I want to show that equilibrium is achieved. So clearly ui of x star is greater than or equal to ui of x minus I star xi. So this is of course obvious, right? None of these elements can actually exceed ui x star. So hence, what is the situation? Each xi star is in fact a best response strategy to x minus I star. Okay. So is this inequality clear? We are told that this quantity that we are looking at is actually equal to the summation of all these, but individually we know that each of these is greater than or equal to this. If individually it's greater, right, and it's equal to the sum of a weighted average, then it must in fact be the case that ui of x star must be greater than or equal to this for all the ones where you pick not the pure strategies but put in this probability. This is the idea. So this is why I have written it this way. A weighted average no bigger than this element can actually, so it cannot exceed this. So this is what says that xi star is in fact a best response to strategy x minus I. That's what it is. Of course, this is true for all of them, so it's a Nash equilibrium. So this is the claim. Let me just show you the claim again, and this is what we'll make use of. So at Nash equilibrium, I just need to look at the pure strategies and look at of Ri. So what do we want? So when you are looking for equilibrium, we are looking for an X star such that for all I and for all options of player I, this is all J, I'm looking for this inequality to hold. The earlier claim told me that this suffices. So that is for all Ij. I can rewrite this as ui star x minus I star pi Ij minus ui x star greater than or equal to 0. This is the inequality that I am looking for. So for a mixed profile that is given to me, I define the following function. Phi Ij of x is simply the maximum of 0 and this difference. Basically, I am going to measure this difference for any x. At x star, I know that this is going to be greater than or equal to 0. In general, I have no idea what it's going to be, right? For any particular x, I just measure this. This is the function that. So it measures how much better off player I would be if she picked pi Ij instead of xi when everyone else's strategy is fixed. This is the idea. For any strategy profile that you give me, what this function picks is for the jth element, for the jth choice, how much better off if I were to pick the pure strategy given by the element j. Yeah, that's what it measures. Well, why max 0 this? Look at this. This is positive. When is it strictly greater than 0? Yeah, when that particular choice is better than the weighted average, right? Picking this pure strategy is going to give me a payoff that's better than the average of the rest, in which case it will be greater than 0. It will be equal to 0 when it's exactly the maximum of these, right? Right. Okay, and it's negative if this particular choice is going to be nasty, it's going to be below the average. There will be some, because I'm always looking at weighted average, right? There will be some choices which will give me below the best payoff, and some choices. So what this does is to keep it positive. That's of course for continuity, that will make sure, right? It's always going to keep it non-negative. So you simply take the maximum of 0 and that. In particular, I am really interested in when this thing is going to become greater than 0. That's what I am after. Okay. So define the following function on the space of strategy profiles as follows. For f of x, I give the new strategy profile, which is what I need to do, right? I am navigating in the space of strategy profiles. Given x, I come up with an x prime. How is that x prime given to me? Okay. So x prime is going to be basically whatever is already there with this added advantage. Don't worry about this other factor for the moment. So this is really what I want to do. I am taking some arbitrary point in my space, which is a strategy profile, and for each player, I look at each possible pure strategy and look at how much better off that player is going to be. And I add, that's going to be the new strategy profile that I go to. If I did that, this will not be probabilities, right? This is really the map I want. Xi prime j equals xij plus phi ij. This is what I would like, right? But of course, I can't do that because this will not be probabilities anymore, because this number could be something crazy. So I need to do a normalization, right? That normalization, what I should really write is simply divided by all the possibilities for phi i's, right? Take the sum of all of them, and that will normalize it to really what I want is this thing. But there is a pathological case where everything is 0. So I don't want to divide by 0, so I put +1 here. That's all. Okay. So I can't divide by 0, right? I have to make sure that when I divide something, that quantity is always greater than 0, non-zero in particular. So I'll make it greater than 0. So everything is going to be non-negative, and in fact the denominator is going to be positive. So that's made sure of. Now you can show that this, in fact this is the probability. Okay, this, because of the way I have weighted it, it's always going to be between 0 and 1, and that's all I need. And you can make sure that therefore it's a strategy profile and it's an X. That's all. Now you can show that f is continuous. Why is that continuous? That's why all this is set up, right? Very carefully. Note that this part, the fact that I have taken the maximum, this function is continuous, right? So each of this is continuous, the maximum is continuous, and then now look at the rest of the garbage I have done. Yeah. So this addition preserves continuity, division by this thing preserves continuity, all this. So it's a straightforward thing. You don't need to do deep arguments. Right? I'm using very straightforward functions which preserve continuity. So by Broward's theorem, it has a fixed point x star. And all we need to show is that f of x star, the one that I have defined here, when it is equal to x star, when it's a fixed point, it's in fact a Nash equilibrium. That's what we need to show. Is the idea clear? Okay. So this is the function. Okay. Now, consider a fixed point x star. What is it that we have got? This is the left hand side. F of x equals x, right? X equals f of x. What is f of x? This is the definition. Just add the phi aj to it and normalize. This is the equation that's available to you at fixed point. Yeah? So what does that mean? First multiply this to this side. So that's all I have done. Xi star at j times this normalizing factor is xi star of j plus phi ij x star. So that means I am saying that this product xi star xj is actually equal to phi ij x star, right? Remember, these are non-zero quantities, right? I mean non-negative quantities. So I can always cancel on both sides, and all I get is this product is equal to phi ij x star. Now this equation, we show that it implies that the right hand side is actually equal to 0. Right hand side is equal to 0 means what? What is phi ij x star? That is the one that measured the difference. It is either it's a maximum of 0 and that inequality, right? That inequality was going to ensure that it's a Nash equilibrium according to our earlier claim. That's how you remember the reverse engineering we did, right? We started with the claim which says that something is a Nash equilibrium, then that inequality holds. What is the inequality? This one, right? So this is what we want. So that's why you're measuring it here. Okay. Yeah. So this is the equation that we need to concentrate on. At equilibrium, whatever is the probability that is assigned by player I for j, right, times this. Okay. So this is okay. So claim. Oh, this is something we need. Okay, this is important because this equality could hold for a very pathological reason. Where is that? This inequality holds because everything could be 0 here, right? If all the probabilities were 0, of course this will all come out to be 0. So you have to argue that there is at least one which is assigned a non-zero probability at equilibrium, some choice. Then only this takes on some weight. Okay. So let me make that claim. For any mixed profile for player I, there exists some choice such that the probability is greater than 0 and phi ijx is 0. Right? It is possible for that phi ij to actually become 0. It's not the case that it's always going to remain non-zero. That of course comes from weighting, again weighted average arguments, but let's keep the claim, assume the claim for now. Let's see. So suppose this is the case, then for such a j, what do I know? Xi star of j is greater than 0 and phi ij x star is 0, and this is the situation here. We have shown that this product equals phi ij x star at equilibrium for all ij, right? Remember this equation that I had in the last slide, right? This product is equal to phi ij x star at equilibrium. Is it clear? Now I am saying for this particular choice, this is greater than 0 and phi ij x star is 0, right? Consider such a thing. Now, what is the situation here? Phi I k x star is greater than or equal to 0. They are all non-negative, and hence for all k, phi I k x star must be 0, because we are told that the product of something greater than 0 and some non-negative thing here is turning out to be 0. That's possible only if all of these are 0. That is, for all choices that player I makes, this inequality, this greater than or equal to holds. This must be the case, right? Because phi I k was measuring maximum of 0 and this minus this, right? So it has to be greater than or equal to 0. But this is exactly what we need. This is what is required, right? Because we proved that if this happens for all I, then that for pure strategies, if this happens, then it's a Nash equilibrium, right? The earlier claim was that x star is a Nash equilibrium if and only if this holds. So this condition will give you Nash equilibrium. So if I prove that claim, I am done. So claim. What is the claim? For any mixed profile for player I, there exists a choice which is given a positive probability and such that when you are measuring how far away, what I get is 0. So why is that so? What is the definition? Phi ij of x is maximum of 0 and this difference. Well, but then I know that uix is the weighted average of all of these, right, based on the weights in xi. Now, when you have got a weighted average, there must be some j such that xij is greater than 0 and this does not exceed the weighted average. That's all. That is, in which case uxi pi aj minus uix is going to be less than or equal to 0 for this, because this one is going to be smaller than uix, right? There must be at least one element which is going to be below the average, and that is the one that I need to take. For this, phi aj of x is 0 as required. Okay. So it can't be that all the elements are above average, right? That's not possible. At best, they can be equal. So equality is always something that you are looking. If that is so, of course, you will get 0. There is no problem, right? All the elements cannot be strictly above, having greater than 0 probability and be strictly above the average. That's not possible. That's what you are doing. So that does the job. Let me just go over it once again, the arguments, and then we can move. Okay. So first, sorry. Okay. So we started with this claim. The claim is that at a profile is an equilibrium if and only if the expected payoff for player I is maximum among all these where you are only looking at pure strategies, right? And once you prove this suggests a strategy for us when you look for equilibrium, right? For any particular profile x, I want to move from x to something that adds this possible advantage, this difference, right? That difference I want to make sure that it's positive. So I want to see how I can go. So that is the function f that is defined. So you are looking for, so look for this x such that this difference turns out to be positive. So find in general wherever you are at x, find that difference. If it is negative, okay, I want to see how far I can go, right? So the idea of, that's what is said here. Look at the current choice that I have made, whatever is the probability that I have picked, right? And see whether I would be better off playing the pure strategy, right? And this gives you basically this map. Xi prime of j is actually xij plus phi ijx, but as I said, you need to normalize to make sure that it's actually in the set x that we began with and showing that it's continuous. So this guarantees the existence of a fixed point. Now you argue that that fixed point is going to yield an equilibrium. And now at fixed point this equation holds, and this equation suggests that, this equation leads us to this equality, It says that in general, if I look at whatever is the probability that I assign to the choice j, right, that multiplied by this normalizing, this is basically the sum of all the advantages that we are talking about, right. So this says that this is what I am doing for option j, this is what I would get by for all of them, the advantage that I have got for all the options, right. These are all my choices, I am summing over them, right, and that equals phi ij, right. So now we argue that if this is the case, it must be in fact true that it's true for phi ij of x star is 0 for all of them. That means that that inequality on the right hand side was always turning out to be less than or equal to that. And this, for this, first we argue that there is at least one pure choice, for one choice that I can make, which is assigned a non-zero probability, and for which this advantage is actually 0. If such a thing exists, now if I plug it in, I find that I am taking something which is greater than 0 and I am multiplying by a non-negative quantity to get 0, and therefore this must be 0. So for all of them this is 0. Now you apply and what you get is a Nash equilibrium. And the fact that such a choice exists comes by the notion of weighted average that we are using. Okay. So that's it. So this is the proof of Nash's theorem. And so what are the important things that we get about Nash, we learn about Nash equilibrium? One is that it's not guaranteed for pure strategies. We have talked about this many times. Second is that there can be lots of Nash equilibria. It's not very difficult to set up situations and show that in fact for very simple games there can be infinitely many Nash equilibria. These are mixed strategies, right? So it's a rich space. So you can have, for various probability choices, you can have Nash equilibria. So even where there are finitely many, when you discretize things and work with them, you can show that there can be exponentially many Nash equilibria. Exponential in what? Let me not worry about it. In okay. So now something that is interesting here. Take the two-player case, two-player zero-sum case, right? Suppose there are two Nash equilibria that you have got, right? Now this is why you say these equilibria are rectangular. Rectangular is the term used. That means that P1, P2 is one Nash equilibrium, P1 prime, P2 prime is a Nash equilibrium. Look at combinations. P1 prime, P2, P1, P2 prime, these are also Nash equilibria as well. It's a nice exercise to show. I mean, just manipulation of the kind that we have been doing. And actually they give the same payoffs. So in the zero-sum case, these are rectangular, that is the idea. And what you get are, the value that you get is unique, right? It's not that, not only do I get, all these strategies, the payoff that I get is going to be the same in all of them. Now, this is not the case in general for non-zero sum. There is another equilibrium. If the second equilibrium is the payoffs are greater than or equal to the first one for all of us, right? And then there is at least one of them where it's strictly greater, right? Then the second one is preferred. Pareto optimal is one where it's optimal with respect to this notion. But a big problem is how do you ensure Pareto optimality? That means that among the equilibria, the one that is chosen will be where everybody is better off, or at least not worse off, and at least somebody is better off, strictly better off, right? So, and that's a very important question in game theory, because many of these things are about setting up interacting situations where the players have some potential for conflict, some potential for cooperation. That's what it's about, right? Then you can ask, why would they play in such a way where everybody should be better off? If you're just selfish, why would you do that? Can you set up the game in such a way that is ensured? That's an interesting question for economics. And next week I'll be discussing distributed algorithms, and the connection between distributed algorithms and games is really, I think, one of the most interesting questions for computer science, because distributed systems or distributed computation is about processes which are proceeding autonomously and making some decision. Classically, distributed computing has mostly worked in cooperative situations, but today when you look at internet, processes that run on internet, There's no reason to believe that these are processes that are going to, these can be selfish agents. You just want to maximize whatever resources that you can get. And there's no particular reason why I have to cooperate with somebody else, right? Yeah, let me come to that at the end of this. So there is some more point. So basically, which equilibrium will be chosen will be decided by the dynamics, lots of additional criteria, structure of interaction. The interaction model that is there in this is pathetic. There is nothing, Autonomously, independently, we all make our choices. We don't talk to each other. We are locked in separate rooms and then we come. It's not like that. Actually, the way games go is that there is signaling, there is some potential, I threaten you, I say if you play this, next round I'll play this. So strategies you don't pick and come. You would like to strategize online, and then what are the implications? This is to tell you that you can develop an interesting theory. The point is that you can mathematize these things and translate it into some kind of geometric questions of this kind and solve. That's the message I want to give you, right? Because these are the basics, but that will get more complicated as you go along. But the basic mathematics is this, and Nash has provided a very nice foundation for this. Now, the specific case of 2% zero-sum games is interesting because you can say a lot more in that case, right? The two utility functions that you've got, yesterday I was already mentioning it to you, right? You can, for the two-player case, I can present it as a bimatrix. If it's a zero-sum, I don't even have to have two matrices because every entry in one is going to be negative of every entry in the other. There is only one matrix involved, right? So the payoff matrix needs to list payoffs for one player only because the other one is negative of that. Player 1 wants to maximize, so there is only a single utility function, right? For every profile, there is a number there. You don't have this mess of tuples that you need to work with. So there is a single number there. Player 1 wants to maximize that number, and player 2 wants to minimize that number. Zero sum is very nice. So this is the matrix view of zero-sum games. So suppose we have a 2% zero-sum game. That means you have an M1 by M2 matrix A. Player 1 chooses a mixed strategy X1 and player 2 chooses a mixed strategy X2. So you got this column vectors. Now look at the product X1 transpose A X2. If you do the calculation, what is this? This is the sum over possible choices of player 1, sum over choices of player 2, and simply the product of the probabilities. Right? The probability that player 1 chooses I and player 2 chooses J times the thing in the payoff. Exactly what I have been writing so far, but particularized for this case. Yeah? Now, this is precisely the probability of the pure combination Ij. Right? So, for the mixed profile X1, X2, X1 transpose A X2 gives me U1 of X, which is equal to minus U2 of X. The expected payoff for player 1, which is equal to the negative of the expected payoff for player 2. Now, there is a notion of so-called mini-maximizing strategies. Suppose player 1 chooses a mixed strategy X1, but trying to maximize the payoff in the worst situation possible, right? What is the worst? I want to look at whatever is the worst, and I want to make sure, I want to guarantee that in the worst possible situation, this is the best I can get, right? This is the, well, the worst is when player 2 picks X2 such that this number is minimized. Player 2 is job is very clear. She is going to minimize the whole thing. So I look at, so I'll say that X1 star is a mini-maximizer for player 1 if I consider all possible choices of X2 and look at the minimum value for this, where I have picked X1 star, right? Plug in X2, look at all the minimum. That is actually equal to maximum over all possible X1, min over X2. This. Is it clear? Here I am looking at, I have fixed my strategy. If by fixing the strategy to be X1 star, no matter what nasty thing you do to me, right? Whatever is the payoff I get is the best payoff I can get. This is the conservative guarantee that I can provide. Similarly, for X2 star, what are you doing? You want to get the best you can get, right? You want to think of the worst possible situation, and in that you want to get the minimum possible value because you are a minimizer, right? So you pick an X2 star where what is the worst you can think of? I am trying to maximize mine. look at all possible x1, look at the maximum over all x1, and look at the compute the value. That should be equal to the minimum over x2 for all possible x1. Right? So now note that this min over x2, x1 star t x2 is always going to be less than or equal to x1 star t x2 star. Why? Because this is minimum over all of them, so it will be of course less than or equal to for x2 star. Right? Similarly, this is going to be less than or equal to max over x1 because it's maximum. So it's going to be of course dominating whatever is here. So at equilibrium, right? Not at equilibrium. If we don't even know that it's equilibrium, okay. If I'm picking the mini-maximizer and you are picking the max minimizer, that quantity, that expected payoff here, that value here is always going to be bounded by these two sides. Right? Amazingly, what von Neumann showed was that that equality holds. And this is the theorem that I was talking about. It's 1928, long before Nash. Okay. In fact, this theorem is what inspired Nash to think about this. If you read The Beautiful Mind, right? And the film doesn't talk about this, but in the book, The Beautiful Mind, Nash heard about this problem, and it was presented to him as a problem because look, this works for 2 players. Do you see already that there is no such thing for 3 players? Think about this. Sorry, non-zero sum. Huh? For zero sum this works. For non-zero sum there is no such thing. Because what is the worst? Here the worst is very clear. I want to think about the worst possible situation and maximize mine. Maximize mine is okay, but what is the worst possible situation is not clear. In zero sum it's crystal clear. So Nash was thinking about what is that? And von Neumann had in fact suggested, though of course he didn't write it, in conversations to various people, that there is a way by which you can come up with what might be the worst. Again by geometric insight, that it's true that even if it's overlapping objectives, even if you don't have zero sum objectives, there must be some kind of minima that you can compute, right? And von Neumann was of course the master of computing minima in arbitrary spaces. So he had some kind of algebraic techniques and so on. But nothing was taking off, and for a long time various people were trying, and Nash was basically studying this proof and tried to come up with a general idea of how this might go. And of course he realized that fixed points was the answer. Okay, so what is the minimax theorem? The minimax theorem, I'm not going to do a proof, I'm going to just tell you how this goes, but it's a beautiful proof and I would suggest you learn. It's a very simple idea, simple proof. So consider a 2% zero sum game. The theorem says that there is a unique value V star, which is that central value, such that for some, this is the maxi-minimizer and mini-maximizer. If I take this value, it's greater than or equal to V star, what I had put in there, and AX2 star is dominated by this, and thus therefore this is actually equal to this. So that is maximum over x1, minimum over x2, x1 transpose AX2 for that matrix is exactly equal to V star and this. So, and of course once you prove this, you can show that these conditions hold precisely when that pair is a Nash equilibrium. Okay. And as I said, I'm not going to do the proof. The proof is 20 minutes or so, but it's worth learning on your own. It's there in many textbooks. The point is, the theorem says something interesting, right? Player 1 is guaranteed at least V star as expected profit, and player 2 is guaranteed V star as the at most upper bound on the expected loss, and this is the minimax value. So the maximum gain that one can guarantee should be always less than or equal to the minimum loss that 2 can guarantee. As I said, so that inequality is obvious, and what it does is this, that it's the same, and Nash equilibrium and this minimax profiles are actually the same thing, because at equilibrium symmetrically each has to be the best response to the other. Now in a minimax profile, if you look at this pair again, this is similar to the support that we talked about, the best response condition that we talked about. The moment I see that one of those, for one of the j's, the value is greater than 0, then I know that that's going to give me the equilibrium value. This is true for each of them. except that we don't know how to compute the minimax value and a minimax profile. This only says that if you find an equilibrium, this property holds, right? If you can find a value like that. But what is nice is that the way it is set up now, it's a very simple calculation. I can set it up as an optimization problem. So what you are saying is, you are given this matrix A, and you are saying maximize the value V, which is subject to these constraints. X1 transpose A for J, for every choice of J is greater than or equal to V. Each of these things sum up to 1, each of these is greater than or equal to 0. That's it. So now, so by the theorem, an optimal solution would precisely give the minimax value and the min maximizer for player 1. So we are optimizing a linear objective under linear constraints. So you can set it up as a linear programming problem, and we have good algorithms for it. So I'm not talking much about computing equilibria, but at least, as I said, for the 2% zero sum case, you get an immediate algorithm. And okay, yeah, so I don't want to go further into this. But what about Nash equilibrium itself? How do you compute Nash equilibrium? Remember that the theorem only talks about existence of Nash equilibria. How do you compute it? Now, if you look at that map that we set up, right, finding something like that and looking for fixed points. In general, how do you compute fixed points? Computing Broward fixed point is in general hard. If I give you a, remember that we are talking about a continuous function over a convex compact space, right? How do you compute such a thing? Now, this was something, of course, people thought a lot about, and there is one algorithm due to Lemke and Hausen in the 70s, which tried to do pretty much like going by this, try to set up a simplex and solve, and something like a simplex algorithm. And that's one, but these are all algorithms that take exponential time. And what is the complexity of Nash equilibrium? This has always been a question, and only recently, in about the last 10 years, it's basically been shown that a very nice theorem of Dasakis, Papadimitriou, and one more person, where they showed that basically it's the complexity of computing Broward fixed points. And that, of course, then you have to go into. And but what is extremely interesting is that 1909 Broward proved this theorem, and it took close to a century, right? By the end, it was the end of the century or early years of this century, where people actually pinned down the complexity of computing Broward fixed points, which of course gives the complexity of computing Nash equilibrium. This is all in the last 10 years or so. Well, that's extremely interesting research, but it requires a bit more background. So I'm not going to do that. But if somebody is interested, the Lemke-Hausen algorithm from the 70s is much simpler. One can go through that, and we could do. But I don't want to take it up now. These are all like later things for me, because I want to talk about connection to computer science. As I said, one big reason why one could be interested in this theory in computer science, there are like 2 or 3 strands from which this comes through. One is the notion of algorithmic game theory. I've already said, here is a question you want to compute, right? You want to compute Nash equilibrium. What's the complexity of that? You know, what are the lower bounds on algorithms that try to do, etc., etc. Another is different game models, right? If I didn't mention it, but if you look at the matrices that I was drawing yesterday, very often these are all symmetric games. Is it that can I exploit symmetry in these matrices? For symmetric games, can I prove something? Okay. Then the so-called degenerate games. So for different subclasses of games, even if in general I can't compute Nash equilibria, can I do better? And the Nash equilibrium is only one notion of equilibrium that we have. Turns out that there are a lot of other, weaker notions. So one is algorithmic questions related to these. And note that since these are tied to optimization problems, there are and we know fair amount increasingly something on optimization problems. How can we use that expertise and solve game theoretic questions? This is one body of work. Second body of work is related to these questions that I keep raising about the model itself, right? Now, game theory has, much better models to talk about things like, then there are things like imperfect information I didn't even go into. These are all things on games of perfect information. But there are other mathematical questions that are of interest, right? What is the input to these things? There is this bloody matrix, right? You've got M1 options for player 1, M2 options for player 2, you're talking about M1 by M2 matrix. If there are n players, you're talking about an n-dimensional matrix. Talking about any algorithm in the size of this matrix is bizarre, because that's going to be already something huge. Can I have compact representations? I shouldn't use compact, that means something here. Can I use concise representations of these? Now, there is this very nice model of graphical games that people have been trying to do, where you say that, okay, in a large game, a player is not going to see everything, right? The player is going to see only some other players. So I strategize based only on what I see of these players. Can I still have Equilibria in these? Okay. Now, Soumya was here. Soumya and I have worked on some models of neighborhood games, where we look at things like there is a kind of a topology where I see only some neighbors. For distributed computing, this is a very standard model. In distributed algorithms, in general, a player makes moves, or a process knows only the state of the neighbors. You need explicit communication to learn the states of others in the network. So you can bring in communication. Now, once you bring in communication into the game model, a lot of fun begins. So you can talk about distributed games where every player is making. So you think of it as, have you played chess on the net? Right? You are playing here. Somebody else is very far away is playing somewhere else. Right? Of course, that's moving on a single board. Now there are also games where each player moves on her own board. Okay, various kinds of board games that are there on the net that you can see, that you move on your own, but then you have to communicate, you have to reveal your moves. In some cases, part of the game is to even figure out what the moves the other guys have made, because you are only allowed some part of these. So these kind of games can be analyzed. And of course the challenge is internet. Internet, as I said, can be thought of as a huge game, right? All these players are selfish agents. Papadimitriou calls understanding why internet works is one of the most important problems for computer science, because it's if you look at TCP/IP, it's an extremely stupid protocol. Right? It's something like I keep trying to send packets. If it doesn't work, drop it. Right? Come on, why should it work? Something like this, but it works. It's the most amazingly efficient protocol that we know. Efficient in terms of being very dynamic, flexible, all that. People have suggested, so let me just take 1 minute. For instance, TCP/IP has this condition which says that whenever there is some jamming in the bandwidth, right? When there is congestion in the network, right? I am asking for some bandwidth, she's asking for some bandwidth, he's asking, and there is some congestion, right? If you voluntarily drop packets, right? If you voluntarily drop packets, then when the congestion is resolved, you will be reallocated, right? You will get priority, is what it says. Now, if you were a player, think of it as a player, right? Asking for something. Why would you drop packets? I would much rather wait for Radheshyam to drop his packets, right? Then the congestion will be resolved, right? Why should I drop mine? But the point is, this is what TCP/IP says, and it works. Now, actually, Rahul Garg and colleagues have actually set it up as a game and show that under some conditions, which are a bit suspect, but if you believe that, dropping packets voluntarily in this sense is a Nash equilibrium. This could be one reason why these strategies are stable, right? Some strategies that you see work, right? The other big surprise is things like YouTube, right? YouTube, when you watch some film on YouTube, where are the files? That movie that it's showing you, right? Where is it? Where is that movie file? Yeah? Do you know? Now you say cloud. Cloud is in fact a recent thing. YouTube is technology came even before the cloud existed. Yeah, but where is it? There is no one remote server which has got all these YouTube files. YouTube would not have taken off if you had to build these gigantic servers, right? So how does it work? It's all over the world, right? Online, that's the reason you can go to YouTube, see the same film today some 4-minute film today and see it tomorrow, and it will come at very different speeds. Because at that time it tries to acquire. And where it is today need not be tomorrow. I mean, that's why, of course, the cloud is a natural implementation today. But the technology started. So it's a distributed file server. And the deal is that once you get in and you become part of it, you volunteer to say, so at the same time, you're uploading files and you're downloading files. So you're hosting your computer for other people to store their files. Other people meaning some YouTube files. And so the deal is that, what would you like to do? Ideally, I wouldn't like to store anything in mine. I would just like to get from everybody else and see what I want, right? But of course, if there is a hub that is watching you, you are refusing always to take on anything, but only you're not willing to upload anything for yourself, right? Store anything, but you only want from others. Then of course, okay, so this is, so it follows a punishment strategy, which says that any guy who keeps saying no to taking on anything but only wants from others, I'll punish. How do you punish, etc., you can think of. Okay, so here is a very interesting game that's going on. It's a really large game, right? But actually it's quite stable. And when people, BitTorrent is one protocol, I don't know if you've heard of. BitTorrent is one which has flavor of this kind of thing. When 10 years ago, okay, these are all extremely recent phenomena. Okay, 10 years ago, when BitTorrent was being discussed and this kind of protocols were being discussed, I don't think anyone would have believed that, these are just some games that academics are talking about, right? Why would anything like this work? But somebody, dared to implement it and it moved on. And what is implemented is not even the best in any way in terms of analysis, but it's something that works amazingly. So we have no idea, what models of interaction and this actually work. So I'm saying from a practical perspective also, these kind of game theoretic ways are interesting, but of course for me, more from a foundational perspective in terms of interacting computations, right? Interacting systems. Traditionally, distributed computing has provided excellent models of interaction. Concurrency theory in computer science has come up with very sophisticated models of interaction. In terms of communication, I would say internet is the most dramatic example that we can think of. I think biology and the kind of signaling that is there in biological systems and internet, these are the two most dramatic models of interaction that we know of compared to anything else, mathematically speaking. Game theory, but distributed computing, the way models are built, they're all cooperative. This kind of competitive things is very, very recent, and we don't have good formal mathematical models of these at all. Game theory is very good at models of competition, cooperation, putting it together, but its notion of communication and interaction is, as I said, pathetic. There's nothing there, So the kind of research that I'm involved in, that I'm interested in, is, for instance, to see where, you can, there's a lot of body of work that is developing now, to see whether this kind of insights from distributed computing on concurrency can be useful in game theory, and insights from game theory can be useful in distributed computing. That's far away. But to even mention what sort of these things, we have to learn a little bit of what distributed algorithms are. So I'm not going to talk about distributed computing, YouTube, this thing, and so on. So in the next 3 lectures, I thought I'll just show you what happens. I mean, we know what kind of algorithms does everybody know? Let's see. Spanning tree, right? I hope everyone knows spanning tree. Sorting, searching, these are all, hopefully, if you don't know, please, I want to be sure of all these things. But the same question now, if you ask in a distributed framework, what's a distributed algorithm for spanning tree, right? That means there is a graph. I can't see the entire graph, right? I can see bits of the graph, you can see bits of the graph, she can see bits of the graph, but somehow can we talk to each other and build a spanning tree for the graph? The problem is bloody non-trivial. It's not simple at all if you start thinking about it. I've got a number, you got a number, and you got a number. We all have to talk to each other somehow, minimize communications, right? And communicate as little as possible and still sort the whole thing, right? So I want to take up some examples. As I said, I'm a theoretician, so I'm only interested in abstract problems of this kind. There is some connection to protocol somewhere, but as far as I'm concerned, finally every protocol is going to do something, right? So we'll look at some distributed algorithms and see how analysis goes in these. And of course, combining that kind of analysis with game theoretic analysis is where we want to get to. That's of course an interesting research problem. So, okay, I'm not going to talk much about game theory otherwise, but for those interested, there is a lot more that I can suggest you can read. Okay. Oh yeah, this is a whole lecture on connections between games and computer science. One thing I didn't mention, but this is for really for people who know a little bit of complexity theory. There are these various complexity classes, right? Polynomial time, P, NP, P space, exponential space, etc. Now, there is actually a formal map between games and complexity classes. So, for instance, chess is a game, it's a two-player game, fixed length, played on an 8x8 board, right? But if you think about it, it's not very difficult to think of it as an n by n board, right? And talk about asymptotic complexity of playing on an n by n board. And then you can show that it's in fact exponential time complete, okay? And so in general, exactly like we talk about games, complexity classes, algorithms and complexity of algorithms, you can talk about games, reductions between games. And by now, there is a project that people have been taking up. So now, pretty much all the complexity classes except P. P is the one that we don't have any good characterizations for. There are game characterizations for NP, P space, all these things with appropriate reductions and so on. So this is a lecture on that. Somebody is interested, I can. But that you need to know a little more about complexity classes. What is the advantage of doing that? That means that this space of games we can classify in a very, very nice way. And in a way where the difficulty of playing the game, we can think of in computational complexity terms, right? And since the randomization is, essentially built into the terminology in game theory, you are really talking about randomized complexity classes, and understanding them is one of the important projects for theoretical computer science. So that is another thing. But even in a very simple way, you can think about it, right? If I were to, there is this game that everybody knows, right? I mean, you think of a 2-digit number, right? I want to find what it is. You can ask any questions except that I'll allow only yes or no answers. How many questions do you need to find it? Log n. Okay, you guys are all dadas, right? I said 2-digit numbers. Okay, so that means within 100, so 7 questions or whatever. But think of it as look at this game, right? Look at this log n game. I've thought of a number less than n, and you are trying to find out what is your strategy for this thing? Binary search for finding it. What is my strategy to force you to ask log n questions? What number should I think of which forces you to ask log n questions? Exactly, I shouldn't think of a number at all, no? You keep asking me, anytime you divide the space into unequal, I'll pick the unequal, the greater one. If you pick something equal, I just randomly say yes or no, keep track and answer. That's the strategy. So this lower bound argument that we had for binary search, I can turn into a 2-player zero-sum game. This lecture is about showing that any lower bound argument is actually a 2% zero-sum game, abstractly, right? Sorting and log n, I can turn it into this, and so it's not an accident that we call them adversary arguments and analysis of algorithms, right? It's actually formally a 2-player zero-sum game. Now, the moment you start thinking about it, in general, all Turing machine moves you can think of as moves in games, right? So that's the connection. So you can think of it abstractly as solitaire games with chance moves or probabilistic computation. You can bring in all that. So the connection between games and computations runs really deep. And von Neumann had this idea, and if you go back to the original papers of von Neumann, remember von Neumann was the person who designed the first computer, that designed the first electronic computer that we know. Okay, von Neumann was thinking in these terms, and he was really taking Turing's ideas and trying to build actual machines. And he suggests in many places that the way to build these guys is probably as games. Okay, so he's got very nice ideas. So in a foundational sense, I think there is a way to rework many concepts in computer science there. Anyway.